Steve, not the one first. Oh, okay. Well, welcome back. Actually, could you clap for them? Welcome back to. Oh, 4:15.
Well, whatever. Just I don't know if everyone's here. People hanging out.
Well, he's going to clap them in. Very good clapping. Excellent. Okay. Well, very good clapping will produce people from the empty set. Your clapping has to improve, right?
You have to learn how to say this.
I hope those of you online will forgive us here. There's nothing but stupidity going on at the minute. We are trying to get our act together. You let me know when you're ready.
Well, I'm ready whenever you're ready.
Okay. Welcome back, everybody, to Stephen's second lecture of the day. So welcome back our online audience. Thank you for coming. Stephen, please. Thank you, Stephen.
Thank you very much. Please don't let me go beyond 5. Okay, so just to recap, this long aside, constructing a Cazul complex, which is a free resolution of just the ground field thought of as a graded S module. So to compute this Tor here, we can then just tensor that with our Stanley-Reisner ring, right? We resolve this, now tensor with this over S, and the S or polynomial ring that was right there will become the Stanley-Reisner ring. We have this differential, still just taking an exterior variable ui to a polynomial variable vi. And that's it. So that'll compute Tor, and even better than this small DG algebra is something called the reduced Cazul complex, where you could consider all the powers, like vi squared, of these polynomial generators, as well as all the ui's vi's, right? Like the differential, notice if you apply the Leibniz rule, takes any of these monomials to this one. So that ideal there is like an acyclic ideal, and we can quotient out by it. The differential just pairs those elements off. So quotienting out by that won't change the cohomology, and it leaves us with something that's just a finite dimensional vector space. So here's like a very small DG algebra that we can use to compute things. And then this, I said, also shows us a way to prove this theorem of Dijkstraper, Panov, Franz, etc. Because now we have very small gadgets that compute both of these things. So on the left-hand side, let's just think of the cochains on ZK. So ZK with some polyhedral product, that's a subcomplex of a polydisk D2 to the M. And if we think of the disk as having like 3 cells, I want to think of like open cells, like let's call them D and S and 1. So D is an open 2 cells. I want to think of that as just like the whole thing minus, the disk minus the boundary. And S thought of as an open cell is like this boundary circle minus the complex number 1. And 1 is just 1. So these are in degree 2, 1, and 0. And then by taking products, we get a cell structure on the polydisk. And so this is going to give us a nice CW structure on ZK. And yeah, we just have very explicit cochains on either side now. So sketch of proof is just going to be like this: D2 to the M decomposes into cells I'm going to call chi I comma j, or any disjoint subsets I and j of our vertex set. So chi ij could just be like all complex m tuples, one zm, where like zi is in disk D in the ith factor, I and I, Zj, you know, is in one cell for J and J, and everything else, Zk, just equals 1. When K is not in the union of I and J. Does that make sense? Oh, okay. Yeah, so this is just a way of parameterizing all these cells, disjoint subsets, I and J. Just by taking products of all of these guys. And then it turns out that Zk is just exactly the CW complex. Those cells, chi, ij, where I isn't just any subset of M, it has to be a face of K now. That's where we're allowed to have like a disk coordinate and certain factors, and J can just be any subset of M, and they have to be disjoint still. Okay, so now let's be very explicit and construct a map. This cell structure in mind. And I think we literally just take like U, let's see, U, J, tensor V, I. By this, I just mean the word, you know, product of all the UJs for J and J, and the product of all the VIs for I and I. Send any word of that length to the cell chi ij. I don't think I need any sign or anything. That's an iso. Yeah, not a quasi-isomorphism, but an actual isomorphism of DGAs. So without quotienting out this acyclic ideal, it's a quasi-isomorphism. But even better, once you quotient that out, this reduced Cazul complex is essentially equal to like the cochain complex of the moment angle complex. So that strengthens this claim of mine that like moment angle complex is just a geometric realization of this Tor algebra. So I'm sort of cheating about something, because usually the cellular cochain complex of a space is not actually an algebra, right? Singular cochains are, but in general, there's not like a approximation of the diagonal map. That's what induces cup products. There's no like cellular approximation, which is functorial and associative. But luckily for moment angle complexes, Bukstauber and Panov showed that there's like a cellular approximation of the diagonal map, which is actually a cellular map with respect to this cell structure we just went over. And so this actually makes sense. And then an alternate, okay, that's the end of like my sketch of the proof, but I mentioned that this result is due to a few people. It's just an aside. An alternate argument would take our fibration and look at the Eilenberg-Mohr spectral sequence. So of the fibration, which I'll write as a pullback, Zk to Djk to Btm. It's over here. So using the formality of the classifying space of a torus, one can argue that this spectral sequence collapses. And the Eilenberg-Mohr spectral sequence, by the way, has like E2 page, the right Tor, because the cohomology of our base here, polynomial ring, that's the S. The cohomology of these two corners on the diagonal, we already proved this is the Stanley-Reisner ring, DJK. Cohomology of a point over here is just our ground field K on degree 0. So it's going to start there, and it's supposed to converge to the cohomology of the fiber. And then again, one has to do something more to get the ring structure, right? This collapse doesn't automatically give you an isomorphism of rings. So plus argument for ring structure. Okay, so I'm sweeping some things under the rug. All of this stuff isn't quite as simple as I've made it out to be. But that's roughly the idea. So let's get to an example. Take a small simplicial complex, like the one on 3 vertices with 1 edge, 2 and 3, say. Okay, so what's our Stanley-Reisner ring here? We've got 3 vertices, so we're looking at the polynomial ring on 3 variables, v1, v2, v3. And we quotient out by the ideal generated by the non-faces. Our minimal non-faces here are just 1, 2, and 1, 3, those 2 edges. And then the Cazul complex of this Stanley-Reisner ring, or let's use the reduced Cazul complex. It's just going to look like this. Exterior algebra on U1, U2, U3, tensor over little k, the Stanley-Reisner ring, the V's. And then we mod it out by this acyclic ideal. So the VI squareds are all 0, and like the UI tensor VI, those are all 0 as well. With D of UI equals VI. Okay, so like I said, this is a very small little thing. You can just compute it by starting to write down D of just a handful of monomials, and that's a basis for the entire thing. So like notice the only things in degree 1 are the U's, right? The U's at degree 1, the V's in degree 2. So in degree 2, all the V's are closed since they're D of U. And then we've just got things like UI, UJ, only other stuff in degree 2. And that's going to look like, I guess I should keep writing U's before V's in order of this tensor product. So like UJ tensor VI minus UI tensor VJ. And then up 1 degree, degree 3, you'd look at things like U tensor of V. So for example, U1 V2. Since 1, 2 is one of our missing faces, that's going to be closed. All right, because this becomes V1, V2, but that's in our Stanley-Reisner ideal, so that's 0. And that's the same thing, or cohomologous to writing the 1, 2 in different order, right? U2, V1, cohomologous to that class. Same with the other missing face, like U1, V3, say. 0 for the same reason. Then there's only like one other thing that could possibly be closed and not exact. So I'll leave it to you, but you should get a picture like this. So we have 1 in degree 0 as basis element. We've got these 2 classes that are closed and not exact. U1, V2, as I wrote it. U1, V3. Then in degree 4, as you might have guessed, you get like U2, U3, V1, say, right? The differential in turn, each U to V, but V1, V2 is 0, and V1, V3 is 0. So that'll represent this top class. Okay, so you can probably guess the homotopy type of this particular moment angle complex. So So that was all method one of computing this Tor algebra, right? This is like a very algebraic way of going about things. And I said commutative algebraists liked this other method called Hochster's formula. So please, yeah.
Just to make sure I'm following the argument in the proof at the top of that middle board, you were saying that we get not merely a quasi-isomorphism of DG algebras, but it's actually an isomorphism, and that was because we found explicit bases on both sides. And then in each degree, you check that the bases match up, and that's why you get an isomorphism of free K modules degree-wise. Was that the argument? Is that?
Yeah, things aren't like free S modules anymore, but yeah, we certainly have
little K modules.
Oh, sure, yes, absolutely.
Yeah, okay, right, because those are, yeah, we do have bases as K modules, well, K vector spaces.
Yeah.
You're saying that RK is actually isomorphic too, so no.
Yeah, I was wondering about the top map. I wanted to make sure that it's an isomorphism of DJs, not merely a quasi-isomorphism.
Exactly, yeah.
Okay.
So if we took just the ordinary Kazul complex, this thing, we've got all these. These all have infinite height, right? So it's not going to be isomorphic to our finite cellular.
That's right. So that's why psychologically I was a bit shocked to see an isomorphism. I think I was thinking of the non-quotiented version where you would just get a quasi-isomorphism.
Exactly. This exact same map would be a quasi-isomorphism from that thing.
Okay.
But even better if we quotient out by the cyclic ideal, do a little more matching.
Yep. Okay. That makes perfect sense. Thank you. And the second question was about the functoriality of the statement in the theorem, because both sides are functors in the simplicial complex K, also in the field little k, but both are covariant, and I'm pretty sure that it's natural. For a big K, as you pointed out yesterday, the polyhedral product construction is covariant in the pairs of spaces and covariant in the simplicial complex with respect to inclusions. If you include a small complex and a big complex, you just include the small polyhedral product into a bigger one.
Right.
Now I take cohomology, it's now contravariant in K. So I'm guessing that the right-hand side wants to be contravariant by saying if I include a small complex and a big complex, well, that means that I now have fewer missing faces. So I think of quotienting out the more missing faces backwards. And I want this isomorphism to be natural with respect to that contravariance in K. Is that right?
Good. Yeah, thank you very much. That's an excellent point. This is natural in K.
Thank you.
Thank you. Yeah. So yeah, that's right. This one's also contravariant. So
would anyone online want to ask a question? Okay, thanks. Thanks, Steve.
Okay, any other questions about this approach? The algebra we spent so much time going over is also going to be sort of the reason this next Hochster formula thing is true. I won't go over the proof in as much detail, but any questions about that before we move to like a more combinatorial point of view on cohomology? Well, let me just state this theorem due to Hochster. It's called Hochster's formula 70s. And it's just allowing you to compute the Betti numbers, I said, of any monomial ring. But I'll just write square free monomial ring, which is a Stanley-Reisner ring of some big K. This is going to be, again, naturally isomorphic, natural in K, to a sum.
Excuse me?
Yes.
There is still problem with the camera. It is not moving.
That's right. You can't use these two boards.
Oh, sure. Okay, okay.
We're sorry about that. We forgot. They're not in the office to switch the camera, so we won't use these two cameras. Sorry about that.
Thank you very much. Let me start over here.
Thank you.
Thank you.
Okay, so I was just saying Hochster's formula describes Tor, which terms of the combinatorics of K in a very explicit way. Be a natural isomorphism of algebras, but the algebra structure on the right-hand side won't be so clear right away. So let me just first talk about, I don't know, graded vector spaces. We're going to have a big sum over all subsets J of our vertex set of the reduced, say, simplicial cohomology of full subcomplexes of K with coefficients in the middle K. Sorry for all the Ks. Yeah, or if you like any, ordinary cohomology of the geometric realizations of these full subcomplexes. So this is where finally you can see how big this class of spaces really is, right? We've got an isomorphism between the cohomology of ZK and this Tor algebra, and Tor can be understood like this explicitly in terms of the full subcomplexes of K. So this is where you see that the cohomology of ZK can look like almost anything. There's some shifting going around, but like you can take any space with torsion, as Tony was saying earlier, triangulate a space with torsion, take that as your big K. And notice that like K shows up in this sum when I take the subset to be all of M. So take any space you like, triangulate it. You could take that as a K and input it into this moment angle functor, and you'll get a space where the cohomology groups of your original space are at least showing up. You can't arrange to have them in any degrees you like because of some shifting going on here. But any sequence, like take the sequence of the cohomology of any space you like, you can arrange for that to show up somewhere in the cohomology of ZK. Yeah.
That's a very hard to get paper, but I have a copy, typewritten, that Foxter sent me. So if anybody wants a copy of Foxter's paper, just write me out. I'll send it to them.
Okay, so both of these last theorems involved some like shifting in cohomology. We said the like ith cohomology group of the moment angle complex is not exactly the homological degree I of Tor. Same thing here. If you put like Tor I here, that doesn't mean putting an I here everywhere. Instead of like tracing through both isomorphisms, I'll just show you that H like N of ZK ends up looking like which pieces of this sum you'll have the reduced cohomology in degree like N minus cardinality of J minus 1, I believe, of that full or induced subcomplex. So in particular, this means that the pth cohomology group of any full subcomplex K sub J is really contributing to like the P plus J plus 1 cohomology of ZK. Okay, so this I think is the useful thing to remember. So this is nice, right? If you understand small dimensional cohomology of the pieces of K, that's telling you all about like higher dimensional cohomology of ZK. As rings, I'll get to the ring structure in a moment, but I won't say much about it. Maybe I should leave this example here for a moment. So like just to see that the Betti numbers are working out, we could look at this example. It came from this simplicial complex. So there's not so many full subcomplexes here. Most of them are contractible, right? Okay, let me just be quick and write like reduced cohomology in degree 0 of the full subcomplex given by any singleton, that's 0, but the full subcomplex on 2, 3 is contractible as well. Full subcomplex on 1, 2 though, that's homotopically a copy of S0. So this full subcomplex, I said 1, 2, should contribute something to what? H0 plus 2 is the size of this vertex set, plus 1 So that's going to sit in H3 of ZK. So as you might guess, this 1, 2 is corresponding to this class 1, 2, and the same thing with the other non-contractible full subcomplex here on the vertex at 1, 2, or sorry, 1, 3. So that's our other generator. And then of course the whole thing, right? That's non-contractible, but still looking like just S0. Here that's supposed to land in 0 plus 3 plus 1. So that's giving us our H4. Okay, this becomes a bit more fun when you have more interesting like sphere triangulations, for example, or bigger simplicial complexes. Because like I said, low degree cohomology of K tells you about high degree structure of ZK. So maybe an exercise. We've already seen what the cohomology of the moment angle manifold associated to this pentagon is supposed to be. Got some connected sum of sphere products. So take that as K and try.
Stephen, what is the effect of that isolated vertex? So you've got something, I want to go back before you go on to a new example. So there's probably general formulas about what happens if you take something or other, and then you just take some isolated point, the way you've done here. You've got the isolated one, which just sits off there by itself. Are there relations presumably known? Is it sort of an algorithm that's easy to see if I compare what I have without the one there to what I get if I add the one there, the isolated vertex?
Well, the homotopy type of these induced or the geometric realizations of induced subcomplexes can change quite a lot when you add or remove a vertex, right? Usually if you have
no, but I'm not talking about adding or subtracting a random vertex. I'm talking about taking something and adding one isolated point.
What's an isolated point?
The one here.
A vertex.
Yeah, one isolated vertex, yeah.
Oh, okay. Yeah.
I know.
Yeah, so that's going to add a lot of noise, basically, right?
Yes,
You're going to
but
get for
what I'm
every other
saying is,
vertex, you have a new missing
Is the
face
noise
now.
understood?
Yeah,
there
I mean,
general
you can write out
formulas for it?
a sort of complicated combinatorial formula. But
So they're not simple formula. And you're saying,
in a sense, I think it's simple, but I mean, the
well,
Betty numbers will
what's the
certainly
form?
get bigger.
If it's simple, what's the formula?
Well, you can imagine how complicated it might be, right? Take, sphere triangulation like this one with a bunch
And
of
add a point.
vertices, and
Yeah.
now you just add in a new vertex out here.
Yeah.
Well, you've suddenly introduced as many vertices as you had originally as missing edges.
Exactly.
So that's giving you a ton of new things in degree
Yes.
3 of ZK.
Yes,
Because H0 of these full subcomplexes
Right.
contribute to H3.
yes.
But also, as you move up, you include those into higher and higher full subcomplexes,
Yes.
and they persist for some amount of time.
Well, but the question was, is there not how complicated, is there a nice formula? Really? Yes, you said there's more to it. There's a lot that's been added. So my question was, is there a nice formula that tells me what the new things that have been added are?
Well, maybe it would satisfy you more if I just said, yes, it is complicated. I don't think it's that complicated because
okay.
the formula is right here, right? And if you
Yeah,
know the
okay.
cohomology of all the original full subcomplexes,
Mhm.
then it's not so hard to work out the cohomology of the new
Actually, that observation, you're using complexes with TDA, that has profound effects, and it stops TDA satisfying certain stability property. That's why this double homology, it gets rid of precisely that phenomenon that we're asking about.
Yeah, that's why I use the word noise, right? If you thought of your original K as some huge data set, unfortunately, adding some outlier that's not connected to anything else really is going to create a lot of noise that you might want to ignore.
No noise. There is no noise.
Santiago,
Oh, that's Santiago.
please illuminate. Is that Santiago?
Yes.
Yes. Yes, we're all ears, Santiago. Let's hear from you.
You are at single point, then the moment angle manifold consists of two copies of the original one.
Yeah, but even more than that, right? Because when you have contractible full subcomplexes like 2, 3 that aren't contributing anything to your original guy, you now have a copy of S0 showing up in your new guy.
Mm-hmm.
Yeah, that's correct.
So I don't know.
It's cross. K is the original. The new K is the original one cross S0.
It could be right. Could be correct.
I don't know, the cross product of special complex with like an isolated vertex. To me, that doesn't do anything, right? If you take a actual Cartesian product with a point, this is more like a, I don't know, disjoint union. Anyway, you can compute everything with this.
You should say at this point that Santiago has his own approach to moment angle complex.
Oh, absolutely. Yeah. When people were asking about smooth moment angle manifolds yesterday, I might have mentioned work of Santiago Lopez de Medrano and Bossio and Meersman, who have this whole other approach to moment angle manifolds. And their work is sort of the only reason we understand the diffeomorphism types of any moment angle manifolds. Okay, so I should stop soon, but I wanted to just get to the stable splitting for polyhedral products today, which will in particular recover this celebrated theorem from combinatorial commutative algebra. So finally, BBCG splitting. BBCG for Bari, Bendersky, Cohen, and Gittler. Need a couple new polyhedral product definitions. So first, let's define for any subset.
Santiago, you have a question, Santiago?
No.
Okay.
Okay, just let me know.
That's a disconnected K. And the moment angle manifold of that K is the angle manifold of the original. It's two copies of the original one.
Okay.
If you take K, so there's a difference between this setup with simplicial complexes and with polytopes. Joins of simplicial complexes are sort of corresponding to products of polytopes, right? You can take the honest Cartesian product of two simple polytopes, get a new simple one, or you can take the join of two simplicial complexes. And the join with like two disjoint points, or the product with an interval as your polytope, that's certainly going to give you just, two copies of the original moment angle manifold you had. Maybe that's where this product idea was coming from. Anyway, let me continue writing. So here's the exact same definition of a polyhedral product where we're just replacing products with smashes. So as usual, yi is going to be either xi or ai. And then we define the polyhedral smash. With this, sorry, there's supposed to be a hat here, supposed to evoke the smash product, I guess. But we can think of it in the exact same way, right? Just the union of all of these things. So union, co-limit over all sigma and k. These guys, or equivalently, this thing polyhedral smash associated to simplicial complex K is just like the image of the ordinary product under the quotient to the smash product. Right, so you could take this thing is sitting inside of a Cartesian product of xi's, quotient that to the smash. This polyhedral smash is just the image of that thing. Now I can't erase that, but notice that, okay, here's a familiar, hopefully, equation. Suspension of an ordinary product ends up splitting suspension of x1, wedge, suspension of x2, wedge, suspension of the smash. So if we iterated this, and suspended an m-fold Cartesian product, we can write that as a wedge over all I1 less than or equal to IP, less than or equal to M, like every possible way of combining all these factors in the smash product. And I just want to rewrite this in a suggestive way. This is equivalently the wedge over just all subsets of our vertex set of these polyhedral smashes. And on the left, this thing, it's just the polyhedral smash where my K is just a full simplex, right? So it has a maximal face, which is just the whole vertex set 1 through M. Just exhaust this union here. So that's just literally the product, all the smash, I should say. Yeah, that's the left-hand side. And the right-hand side I can rewrite as follows. The suspension of these polyhedral smash products, each full subcomplex, K sub I. Did I get that right? So I think that suggests that something much more general might be true when I just put any K here instead of the full simplex. Right? Notice the A's aren't really playing any role here. Each thing over here is just looking like a product of the certain xi's. Or maybe should have a point here for my A's. But anyway, here's the more general thing. And I'll finish with this for today. But the suspension, just any polyhedral product at all, splits stably, but even better than stably, just a single suspension is required. So we have a big wedge for all subsets again, just the suspensions of these polyhedral smash products. So here, each K sub I, an induced subcomplex, only has so many vertices, right? Big I vertices. And I want to reduce the sequence of spaces appropriately, right? Yeah, thank you. The hat is on this side. So I'm just saying I want to restrict only to the relevant spaces over here. I won't introduce notation for that, but our sequence of spaces is supposed to have as many vertices as the simplicial complex we're raising to. Okay, so to prove this is like the most general theorem. It's not so hard to do. But the real interesting part of the splitting is in identifying these spaces. BBCG in various cases of like X's and A's, for example, when A is contractible, they identify these stable summons in a certain way, or when X is contractible, so that's the point, the case when you're looking at like D2S1, for example, you can identify these in a very explicit way and sort of read off these stable summons in terms of the combinatorics of K. And it's kind of fun to go through some of that, but maybe I'll stop here and quickly give the more explicit formulas tomorrow, right? So at the moment, this is just some stable splitting, but it doesn't seem so useful unless we know more about these spaces. And one can have a lot of control over them in terms of the combinatorics of K in various cases of interest. Okay, so let's stop
Thank you,
there. I'll
Stephen.
answer questions.